Hello everybody and welcome back. So, in the last lecture we have been talking about the synthesis of the peptides, short sequences of the peptides, and we have started with the solution phase peptide synthesis, and I have shown that you have to do certain amount of protection and deprotection chemistry in order to restrict the formation of the byproducts which are not desired ones, and I have shown how to protect the amine terminals as well as the acid functional groups. So, once again for the amine terminals, if you want to protect the amino groups of the amino acids, this is your amine. So, amine group, you can protect it either by using Bock anhydride, that will give you this, and then NH Bock O tertiary butyl. This is the Bock protecting group that is usually used for the protection or inactivation of the amine group. Now, how can you deprotect it? You can deprotect Bock. Usually we use a very mild condition for the deprotection of this. You can use TFA. TFA is trifluoroacetic acid. The structure is CH3COOH, CF3. CH3 is acetic acid, CF3 is trifluoroacetic acid. TFA means trifluoroacetic acid. If you treat this at room temperature, then your Bock will be cleaved. How does it work? So, I will write the product first, this, and then you will get back your amine. So, it is a deprotection. So, this is the Bock protection, and here is the Bock deprotection. Now, RCOOH, this is your NH CO. So, if you treat this CF3 COOH, this is an acid. So, basically it will protonate this oxygen here. This will be OH plus. So, this is a acid based deprotection. Once this is formed, now the reason why tertiary butyl group is used is because the tertiary carbocations are pretty stable. So, once this is protonated, it will be attracting the electrons, and it will give you the formation of a tertiary carbocation plus R COOH, you have NH CO and the OH. Now, you had formed initially, if you see, there was one proton transfer from the trifluoroacetic acid to this oxygen. So, this has become a acetate anion, CF3COO minus. Now, this again a proton transfer will happen from here to there, and it will become a OH, either a minus or it can happen instantly. So, the moment this is formed, this will easily decarboxylate minus CO2. I have written it stepwise, first this, then this. It can happen at the same time, that this will take up this proton and then this will go here, this will be eliminated. So, minus CO2 would be eliminated, or carbon dioxide would be eliminated, and that will give you the NH minus followed by the protonation again will give you the amine back. So, that is how the deprotection of the Bock works. So, if you want your system, if you want the deprotection to be happening in acidic condition, then you use a Bock protection group. The second, we have seen that you can use the F-Mock chloride also, right. That is also a amine protection. NH2, if you treat this with F-Mock chloride, then you have NH. What is the structure of F-Mock? CO, O, CH2, and here you have so this is your F-Mock part. This is the protection, and that actually inactivates the amine, the NH group. Now, how to deprotect it? Deprotection of F-Mock, usually done by using mild base. We usually use piperidine. Piperidine is a mild base, it is a Lewis base actually. So, very mild base. In presence of the base, it can be deprotonated to give you the free amine. So, deprotection of F-Mock occurs under basic condition. Deprotonation of the Bock group we have seen occurred under acidic condition. So, this is a big difference, and depending upon your requirement, what kind of peptide you are synthesizing, what is the sequence of your peptide. Sometimes you need to choose the acid labile system, sometimes you need to choose the basic labile system. So, depending upon your requirements, you can choose whether you want to go for F-Mock chemistry or whether you want to go for Bock chemistry. So, how the mechanism works? Double bond here, here is another double bond, here is another double bond, there is another double bond. So, it is a aromatic system, fluorine system. So, in presence of base, Lewis base actually, this is Lb. So, here if you see, this proton is actually pretty much acidic, because negative charge here can be delocalized over the 3 rings. So, that is a stable aromatic system, the negative charge can be delocalized, that makes this proton acidic. So, if you have a base, lone pair of base will take up this proton. That will create a negative charge here, and that actually is the rate determining step. The attack of the base to this acidic proton is the rate determining step of this reaction. So, it generates a negative charge here. So, negative charge goes there, obviously, that comes here, goes here. So, again it will release a molecule of carbon dioxide, and it will form double bond. This is the intermediate or side, this is the product that is formed, intermediate product that is formed. Again this will be reacting with something, if you have the other stuffs, will give you a stable compound, plus your desired free amine. So, that is how the F MOC is deprotected under using the piperidine. Now, usually when you do solution phase chemistry, FMOC chemistry is not that much preferred. BOC chemistry is more preferable compared to the FMOC chemistry, because in the solution phase you have piperidine there and FMOC is also released. Piperidine is hard to be removed from your container. So, that is why this is a difficult part to remove piperidine even by repeated workup. So, in that sense BOC is better. So, next comes the acid we have talked about, right. That you can use the esterification basically. You can do the esterification to this acid to produce the protected carboxylic acid, and I have mentioned that you can use either ethanol for the esterification, or you can use the benzyl alcohol as well. That will give you CO2ET, or if you use this, this will give you NH2CO, CH2PH, or sometimes also you can use the tertiary butoxide protection. If you use tertiary butanol or the other reagent, you can also go for CO2 tertiary butyl also. So, all these are actually, as I have said, that it can be removed by hydrogen palladium reduction. Moreover, apart from that, they can also be deprotected by simple ester hydrolysis that requires two steps. First step, for the hydrolysis of ester, what you need is sodium hydroxide. You need a strong base, and it occurs at room temperature around about 3 hours. If you keep, then your ester would be hydrolyzed. If your ester is hydrolyzed, then what do you get? At the beginning, you get a carboxylate anion. If you have an ester OET, for example, if you hydrolyze it, base catalyzed hydrolysis, if you remember, sodium hydroxide, then so basically it will cleave it. So, OH minus, right. The reaction is this. You will have OH minus plus OH plus ETO minus. Obviously, this is acidic, so this will transfer the proton here, and in the equilibrium what you get is O minus plus the ethanol. That is what is your standard base catalyzed hydrolysis reaction. So, that usually gives you a carboxylate anion. So, you will have a carboxylate anion first here, and then you have to neutralize this using hydrochloric acid. We usually use 1 normal hydrochloric acid, that will depend upon your substrate and how much amount is there. So, you have to acidify it, that will give you the carboxylic acid. So, it actually includes 2 reactions. One is treatment with the strong acid sodium hydroxide, followed by treatment with hydrochloric acid. So, base, then comes the acid. So, that is another way of deprotecting the ester group that is present in the amino acids, and this is what we usually use in solution phase chemistry. Now comes the coupling reagent that we have talked about. I have stopped there in the last lecture. So, there are several types of coupling reagents, and the variations are because of different factors, like some will induce more racemization, some will induce more racemization, less racemization, and so on, and there are other factors involved which I might be talking about. So, out of the several coupling reagents, this is one of them, so with a simple structure, and then you have BOP, widely used. HA2 is very widely used, HB2 is also quite well known and popular. So, I will show you 2 mechanisms, one is for DCC, how it occurs with DCC, and then with the HA2 HATU. And as I have mentioned in the last lecture, that all these coupling reagents are aimed to activate the carboxylic group. So, let us say you have an amine group, you have this amino acid R1, and you treat this with DCC, and DCC always requires a slight, again a mild base, and you can choose a different types of mild base. In this case I have chosen DMAP, it is a pyridine derivative. You can look up the structure. DMAP is a mild base which has a pyridine moiety in it. So, at first what happens, because of the presence of the base, and DMAP is used as a catalyst. You do not need equivalent quantity, you need just a little amount of it. So, in presence of the base, which is DMAP in this case, you get a anion here. So, instead of writing the amino acids all the time, in general I am writing it as just the carboxyl part, and here is R, that means the all of it. So, you have now the anion with you. Now comes the DCC. This is the structure of DCC, dicyclocarbodiimide. Is one of these would be eliminated, and it would take up the proton. So, what you have now is C O COR, here you have N and the cyclohexane ring. Here you have this. that is one of the intermediate. Now, in presence of a slight amount of acid H plus, this gets protonated. So, this should be NH plus and you have this C should be O COR and here there was N and the cyclohexane part, there is N cyclohexane and this N is protonated. Now, we have the amine. Let us say you have taken another amino acid, I am just writing R for the amino acid part, it is R prime, R dash here. So, now this is the activated carbonyl activated complex. So, this would attack the carbonyl carbon, this would come here and this is the driving force for doing that. So, what you now get is R prime, or if I write from the R part R CO NH R prime, you have your peptide bond formed, plus you have the side product, that is this. If this is NH2, if this is NH2, then this is urea. So, this is a derivative of urea. That comes out as the byproduct of the peptide coupling. So, this is your coupled peptide. So, that is one. And now, if you use the HATU, how the mechanism goes there. HATU has the structure it's a cyclic triazine, O minus, that makes this plus, and here dimethyl group N dimethyl and here is NN dimethyl. This is aromatic. This is the structure of HATU R2. Same I consider that you have taken the acid, general acid, instead of writing the amino acid you have the carboxylic acid and the carboxylic acid is existing as carboxylate anion, that you can find, already I have shown you how to obtain this. Again for this also you need a little bit of amount of Lewis base. So, you have a negative charge here, you have an electron deficient carbon here. First attack is this. This is O COR in, this becomes a neutral now. Now, once this is formed, there is another factor that this is electropositive, this nitrogen is positively charged. So, this will drag the electron density towards it. this forces this bond to be cleaved. So, what do you form? You form this. This becomes O minus, this becomes neutral, and here you have a double bond, plus you have this carbon and you have O CO R. You had a CH of course here. Next is this negative charge attracts the carbonyl carbon and this opens here. So, you have this is eliminated as an again a urea derivative. So, you have O double bond over here. Here now you develop the new bond with the ring and the ester. This is your activated carboxylic group. And here I will finish. Now, if you have the amine which is R NH2, this will react, this will come back again, it will be regenerated to some extent, the O minus would be relieved and you will have your this is R, this is R1 CO NH and R1. So, your peptide bond is formed. That is the rough sketch or the mechanism for how the coupling reagents are involved in forming the peptide bond or in activating the carboxylic group. Okay. So, now this is for the chemistry. Now, we will be coming to the solid phase peptide synthesis. Solid phase peptide synthesis, or in short we call it SPPS, is of course as you know it is the synthesis of peptide, how peptides can be synthesized, but we do not do it in solution phase, rather in solid phase. Solution phase, the problem is I had shown that when you are going for multiple steps, more number of amino acid residues in the peptide, in every step you are forming multiple products and all of them would be carried forward. If you cannot purify them in each step, then all of them would be carried forward to the next step and then will multiply. So, you will have a number of side reactions going on apart from your desired product, that is problem 1. Second problem is the problem of racemization. If you see, this is your amino acid, here there is a hydrogen, right, alpha hydrogen, alpha H. So, whenever you are doing the reactions of peptide coupling in the solution phase, you are using a set of reagents, you are using sometimes acids, sometimes base along with the coupling reagents, and depending upon your side chain, this proton has some kind of acidity. So, in presence of reagent, transiently I should write it as reversible reaction. It forms sometimes slight amount of carbon ion can be generated depending upon your reagent and depending upon the acidity of the alpha hydrogen. The moment it generates, of course, it is not very stable. So, it will come back to this phase. it will take up the proton back and will give you the amino acid, but in the meantime it changes its configuration. If this is of L configuration, here there is no configuration. So, when this is taking up the proton back, it can go to L, in that case you will get your original amino acid, or it can go to the deconfiguration, because the H plus can come from either direction. So, that will change the stereochemistry of the amino acid sometimes. So, you will have DL mixture, that is called the racemization. So, although you have started with the pure L amino acid, there is always a high chance of getting a DL mixture of peptides that you do not want. That can be minimized in solid phase chemistry if you do the peptide coupling in solid phase. So, that is another advantage of doing the solid phase chemistry. Third one is of course the ease of purification, that every step you can just wash away. We have seen in DNA case that when you have been doing the solid phase DNA synthesis, because the reaction is happening on a solid support, all the other reagents that you use on top of it, after the reaction is over, you can just remove them by washing. So, those are the advantages of solid phase peptide synthesis. And by the way, solid phase peptide synthesis has earned a Nobel Prize in 1984, and Robert Bruce Merrifield is the person who received Nobel Prize for his solid phase peptide synthesis protocol in chemistry. He is very famous person actually, Professor Merrifield. He has developed many other techniques, not only the solid phase peptide synthesis, but overall solid phase organic synthesis. So, the steps of the solid phase peptide synthesis can be divided into these 4 roughly. The first step, this is wrong, it should be 1984. So, this slide as well as the next slide, this picture I have picked up, these are actually the book content from the Miller and Tanner. Okay. So, the first step of the solid phase synthesis is that the first amino acid residue is coupled to reactive group X attached to an insoluble matrix. I will explain via its free carboxyl functional group. The amino acid residue is otherwise alpha N protected and at other functional groups as appropriate. This means the side chains should be appropriately protected also. That is the first step. It basically says that in the first step, if you have the solid support S, this has a linker, it is connected to a functional group X, and then you attach this with your first amino acid. Let us do a FMOC chemistry here. You attach it with your first amino acid through the carboxyl, so that you get, you can do the other way around also, but we usually do it this way, O CO, this is R NH FMOC. This is very important. This is very important. So, that is how the first amino acid would be attached with the solid support. Now, your amino acid is on a solid content which has the amine group protected FMOC, and we will all the time use the same monomer from now onwards. So, the N protecting group is selectively removed Of course, you have to do the reaction further. So, next step is the removal of the FMOC group, as I have shown before that it can be removed by using piperidine from the alpha position, and then a second alpha N protected amino acid is introduced and activated for coupling with the first amino acid bound to the resin. So, this would be coupled. Then once the peptide link is formed, the process of alpha N deprotection and amino acid coupling continues for as long as required. So, you can recycle the steps, that is the completion of a cycle. Here one reaction is finished, then you add the second monomer, then the third monomer, and it can go on. Once everything is finished, finally the desired length peptide is cleaved. You need only your peptide, so it has to be removed from the solid support, is cleaved from the solid support by chemistry conditions suitable to cleave the linkage between solid support and peptide chain. So, depending upon what is your solid support, the which kind of solid support you have used and which kind of linker you have here, you can choose the appropriate chemistry to break this bond and remove all the amino acid side chain protecting groups as well. And in the last part, you also need to remove whatever the protecting groups you have used on the side chains. So, these 4 are the primary steps for the synthesis involved in the solid phase peptide synthesis. This is the rough sketch, that you have the solid phase, this is a linker actually, and that is how the first amino acid is connected. Here there was one chloride. So, if you use this acid, then you will have first this formation. So, first amino acid is attached here with its FMOC protection. The next step is the deprotection of the FMOC, so that you get a free amine group here, and now you add the monomer. This is your monomer, that is very important. The monomer is the free acid and FMOC protected amine, and every time you have to use this monomer only, where the acid would be free. This is what? Acid NH FMOC. This is your monomer for peptide synthesis, solid phase peptide synthesis. So, you use this along with the coupling reagent, then you will have the peptide bond formation, this peptide bond, and again a FMOC. Further, in the next step again you cleave the FMOC, add another monomer with a different amino acid and continue it. So, once you reach your number of sequences, once you add finish adding all the amino acids stepwise, then finally you have to need to cleave this bond here, that is a global deprotection to remove the solid phase to get your acid C terminal back, and at the same time it is a single step basically, where you can cleave this bond as well as all the protecting groups that you have used on the amino acid side chains. So, if I write down the steps, let us say you have taken a solid support, solid support. This is usually are resins. There are different types of resins available for peptide synthesis, like HMBA and others. They have different functional groups. They are the different resins are, they vary in their functional groups that are there. So, in general I will take here one X, let us say a chloro. It can be a chloro, it can even be an amine. R1 NH FMOC. So, this is step 1. This is reaction between this chloro and this carboxylic acid. So, you will have O, CO, R1, NH, FMOC. If you use amine, then you can have a peptide coupling. NH, CO. So, you have to use the peptide coupling reagent here. If you have an amine group, then it will have the amide bond here. In that case, you will have hard time cleaving this. Well, in those cases, it cleaves the somewhere else, and you get NH2 free, amide free at the C terminal. NH FMOC. So, that is your first step. Step 2 is deprotection. So, step 1 is actually attachment. To solid support. Step 2 is the deprotection. Your solid support is there. I am taking the first one OCO, NH FMOC. You have to use piperidine. Since you are doing the solid phase reaction, piperidine use is not a problem, because once you remove this, all the piperidine that is present in solution can be washed away. O, CO, R and free NH2. That is step 2. Step 3 is coupling. So, solid phase OCO R NH2. Now, you add your second amino acid, this is R1, 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 R2, FMOC protected, so that this amine does not react. So, now you have acid free here, you have amine free here, and they can be coupled, and this is your monomer. So, every time you will use the same different amino acid, but the same FMOC protected and free acid, this and coupling reagent. O, CO, R, NH, CO, R2, NH, FMOC, and likewise you can continue. Finally, step 4 is removal from the solid support, and that reagent varies. So, I am not writing that, and that is how you can get your short sequences of peptides. So, this is all about the solid phase peptide synthesis, and now I will move on to the other part, that the peptide based therapeutics. What good the peptides do in understanding or in their applications. in understanding biological properties or in their applications. And we have already seen some of them that I have talked about in the last lecture, that there are many peptides that show targeting efficiency, such as CRECA peptide, RGD. CRECA is tumor targeting, RGD and NGR, these two were tumor homing. Then polylysine containing or polyarginine containing peptide sequences were good for cell penetration and known as cell penetrating peptides. We have similarly shown that blood brain barrier peptides are also there. So, these peptides are indirect applications for as therapeutics, because they themselves may not have, or they themselves are not that much efficient in curing a disease. These are not the medicines, these are not the drugs, but they help the drugs or other stuffs to be carried over to specific positions and to get into the cells. Now we will see there are many number of peptides that actually can act as medicine itself. They are also in the market. You can find many of them, many of the peptide based medicines in the market. Most of them are present as injections. So, they are themselves medicines or drugs. So, this peptide leuprorelin has this structure. It is a peptide, of course, you can see short sequence. If you start from here, this is a proline, this is arginine, this is leucine, another leucine, tyrosine, this is serine, this is tryptophan, this is your histidine, and this is not a natural amino acid. So, this is a modification part, this is slightly modified peptide. So, this molecule is used as anti-cancer agent to treat prostate cancer, breast cancer and other types of cancer also, and it is a marketized drug. So, it basically acts as a kind of a hormone, and this is administered as an injection. Currently, there are around 60 peptides that are used as medicines, that are FDA approved medicines present in the market, and they have a huge turnover, billions of dollars actually. For example, this drug has a annual turnout of around $7 billion. So, 60 number of peptide based molecules or peptide based therapeutic agents are present in the market, and they are used as medicines. Approximately 140 peptides are currently in clinical trials, and more than 500 peptides are in preclinical development. That means they have shown the efficacy, they have shown the activities, but they are not yet into the last stages of clinical trial. They are at the beginning of their clinical trial. So, these informations I have obtained from this journal article. So, I work also on the peptide chemistry, and we also have developed some of the peptides. I will not show it here. Some of the peptides for different for which can act as a therapeutics. So, this is another example of another peptide named as cyclosporine, or this is also named as cyclosporine. This is basically a cyclic peptide with a modification, cyclic peptide. This is not only a synthesized peptide, this is also a natural product. It is obtained from natural source from a certain fungus, and that shows that is used as immunosuppressant drug. And very importantly, nowadays a very hot topic in the peptide chemistry, in the peptide designing, is to break the protein aggregation, which is a major cause of Alzheimer's disease. And this type of peptides are known as beta breaker peptides. So, Alzheimer is a notorious disease which usually happens in old age, and one of the cause of Alzheimer is the formation of amyloid fibrils. Fibrils means fiber formation. Fiber means they are not soluble in the body. If the proteins becomes fibers, strong fibers, they do not become soluble and they cannot function. So, they will be deposited in the brain cells. So, Alzheimer is the basically the problem in the brain cells. So, proteins get deposited in the form of fibers in the brain cells. So, that stacks it up actually, and this is the amyloid proteins, which actually most of the times it is the amyloid proteins which forms the fibers. So, basically aggregation of the peptides. You have seen earlier how the beta sheet structures are formed in proteins with the stacking, layered by layered stacking interactions, right. So, those kinds of aggregations are responsible for the formation of the fibers. Here you can see, if you have this kind of, this is the primary sequence, this is the folded structure, and then it forms, they starts aggregating under certain conditions and form the fibrils, and then you have the fiber formation. Basically that does not move, that is not becomes insoluble. This is a picture that shows how the fibers are formed. So, fibrils are the aggregation of amyloid beta peptides. Beta is a part of the protein structure. I have also mentioned this before. The whole protein structure, when you consider the whole protein may not have a fully beta sheet structure or fully alpha helix structure. A part of the protein will remain as alpha helix, other part of the protein may stay as beta sheet structures. So, this in this case amyloid beta peptide, the part where the beta sheet conformation occurs, that is responsible for the aggregations because of the layered structures. So, the cure is that to break this fiber formation, either to break this fiber formation or to prevent such kind of fibers to be formed. So, both ways. And nowadays people are developing, trying to develop good peptides, good peptide sequences, synthesized peptide sequences which can block the formation of the aggregation, or after aggregation which can break the aggregation also. So, those are called the beta breaker peptides. There are some popular ones, of course, none of them has come to market yet. For example, KLVFF is one kind of peptide that shows that has the tendency to break, that can break fiber formation, that can break the fibrils. So, K is your lysine, L is leucine, V is valine, phenylalanine. Similarly, L, P, F, F, D also does the same thing, they break the fibrils, or they are inhibitor of fibril formations. L is leucine, P is proline, F is phenylalanine, aspartic acid. So, there are many other examples available in the literature, you can go through it. So, with this I will conclude the synopsis of module 6 and 7. Module 6 I have not shown the summary. So, in these two modules combined, what we have talked about, that we have seen how the sequencing of proteins can be done using the Sanger's method as well as using the advanced degradation method. And out of this, advanced degradation method was used for stepwise cleavage of peptide bonds. So, it is the key method that is used for protein sequencing. Then we have seen how we can break the full protein into its fragments, shorter fragments. and there are chemical methods for it. For site specific cleavage, there are enzymatic methods for it, where the selective hydrolysis happens or selective hydrolysis of the peptide bond occurs, so that you can break a protein into its smaller peptide fragments. And then now we have seen the chemical synthesis of peptides, both solution phase and solid phase peptide synthesis have been shown. And finally, we have given a little bit of idea or little bit of the application part, how the peptides can be used as therapeutics. So, this is all about this module 6 and 7, and then next lecture we will start the new module. Thank you.